disulfides, and sulfides. So we're moving from our oxygen-containing species to sulfur. When we look at thiols, that's going to be our SH compounds. Disulfides are going to be a sulfur-sulfur bond, and then sulfides are going to be, so if we think about this, this is the thiol is the sulfur version of an alcohol, right? The sulfide is the sulfur version of an ether. And then the disulfide is our peroxide. So kind of think about that as equivalents. If we look at thiols, and those are going to be looking at thiol naming system, you know, this could be ethane. Thiol is going to be the name for this one. You know, if we looked at a couple of others, here we have 3-methyl 1-butane thiol, right? And so we have the A for the single bonds, and then we have to add the E back in so that we don't have the N and the T next to each other. So that's why we put the A back in. But this is being named as a thiol, so the thiol should get the lowest priority. When we look at the next one, now we have an alcohol and a thiol. The alcohol is going to get priority. Okay, so therefore we need to name the thiol as a side group name. And for the side group name, this SH, and again, the squiggly line here means attached, is going to be known as a mercapto. And that comes from the original name of sulfur-containing compounds, which was mercury capturing. So mercapto from the Latin, because sulfur-containing compounds would coordinate to mercury. And in fact, one of the best ways to clean up, or one way to clean up mercury, is to actually use sulfur dust. So you can use just plain sulfur, mix that with mercury. And so if you have a little mercury spill in the labs, we used to keep a bottle of sulfur around. We'd sprinkle the sulfur on it, and then that would combine, and we'd be able to get the mercury up. If not, the mercury runs around like, well, like really fast ball bearings. It's just a drop of mercury, it's liquid. Okay, so if we name this one, sorry, I may get into a lot of stories today, but if we look at this one, right, we have 3-mercapto, 3-methyl, 1-butanol. Right, so we're naming it as the alcohol, mercapto being the SH side group name. If we look at disulfides, there's not a lot on disulfide naming systems. Most of your disulfides that you're going to see in this chapter are going to be symmetric. And in a symmetric, we really just name it as the disulfide. So the common name for this one is diethyl disulfide, and that's what you're going to see pretty commonly for these. And then if we look at, and I don't know why I made a longhorn out of this compound. Let's see, let's do this. Okay, so here again, if we're naming it like we would a ether, this will be diethyl sulfide. So for preparation of thiols, we really are looking at just review of SN1, you know, SN2 and SN1 reactions. So these are both review. We can take, you know, a primary bromide react that with a good base. I mean, a good nucleophile. The thiols are great nucleophiles. I even go further than just saying good nucleophiles to great nucleophiles, and they're not very basic. Now they'll accept a proton if you give it one, but they're not going to extract the proton. Okay, so we have this then gives us the sulfur, right? So if we look at the mechanism on this one, we take our bromide, we get backside attack. This is an SN2 type process. Actually, in this case, it's not an SN2 type process. This is an SN2 mechanism, right? And we get the sulfur going up. Okay. One of the differences with the sulfur containing compound and the oxygen derivative of that is that for a secondary group, right, we really have no competition with E2. So what we would have seen in oxygen, if we try to do this with sodium hydroxide, is in oxygen, the sodium hydroxide would be a good base as well as nucleophile, and we get competition with E2. With sulfur containing compounds, we really don't see that. We do see inversion, right? And that's because this is SN2. Okay, so if you think about this reaction, this is review, right? So preparation of thiols is just a review of it as SN2. We can also do an SN1. SN1s really only be favored if we have a tertiary group. And instead of using the sodium thioate, we end up with this, the hydrogen sulfide, and that gives us product mechanism here. We get an SN1, so the first thing that happens is leaving group leaves. That gives us our carbocation. Right, so we get our nucleophilic attack on the carbocation, and then we'll just get a proton abstraction. The thiol. Questions about this one? And this is SN1 mechanism. Right, so this is review as well. So sulfurs make really good nucleophiles, not very basic. So that means it's easy to make thiols with just sodium thioate or a hydrogen sulfide. For disulfides, what we're going to be doing is taking two thiols, reacting that in a mild oxidant, and in this case is the Br2. And we end up with our disulfide. So our mechanism here, we're going to have it react. First thing that we do is get a proton transfer with our base. Okay. Once we have the sulfur negative, then that can react with our bromine. Remember that the bromine could be partially positive, partially negative by an instantaneous dipole. Oops, not too negative. So the negative comes in, acts with the bromine. Ending with the bromide here. And then at this point, then another negative sulfur compound from the base, right, can come in, attack that sulfur. So we've actually oxidized the sulfur at this point. Now we get a, at the bromination, we get a sulfur oxidation, and then that gives us the disulfide. We'll go ahead and do reactions of disulfides here. So if we look at this one, we are adding a mild reducing agent. Yeah, we'll look at thiol reactions in just a minute. It turns out the main reaction for thiols is preparation of sulfides and disulfides. So we're using this, so you could refer to this disulfide. This would be our first reaction. You know, this is a reaction of a thiol. Right. And then preparation of sulfides is going to be reaction of a thiol. So good question. I just didn't put it in that way. So reaction of disulfides is just to go back to the thiols. Okay, it turns out that this one is important. There's a couple of amino acids. You know, so if we think about proteins, there's a couple of amino acids that have thiol components on them, right? So those thiol components with a mild oxidant can then cross-link. So most interactions, structural interactions of proteins, is going to be hydrogen bonding. So if we think about alpha helixes and beta pleats and the 3D structure of tertiary and quaternary being two enzymes. But if we look at the tertiary structure of a protein, in most cases it's hydrogen bonding. In this case, there's actually a covalent bond, right? So we have amino acid moieties, you know, with mercaptan side groups, so thiol side groups on them, right? And then those can then, through a mild oxidant, be created to covalent. Right? It also turns out that most of us have experienced this, right? We can take, where you might have seen this, I grew up with four sisters, so this happened, you know, on a somewhat routine basis. And back then, when I was a kid, perms were a big deal. What a perm is doing is taking hair, which is proteins, and adding an oxidant to them that will allow them to cross-link. Now, they are called disulfide bridges, right? So these are disulfide bridges. Good question. and they give you a covalent connection in your 3D structure. So if you take hair that is straight, that straight hair does have some thiol containing proteins in it, but usually not a lot. You can force it to cross-link by adding an oxidant, a perm solution, which is going to have a mild oxidant in it, and then that will allow it to cross-link. So you force it into circles, right? Hopefully getting two of the sulfur compounds closer together, and then add an oxidant to create the disulfide bond. That then hopefully will cause that hair to be curly, and it's permanent because most times what you're doing with a hot iron is you use the hot iron to create curls, but it's not permanent. It'll wash out. So if you do the chemical oxidation permanent, then what you're doing is that my house, every once in a while, they smell bad. They smell bad because if you put too much oxidant in one place, what that does is oxidize the sulfur, not to do this, right? But all the way to sulfur dioxide, which is the smell of rotting eggs, right? So that's what happens if you're not careful. This also is it's not acid and zinc. Please do not go take your hair and put acid and zinc on it. But relaxation is actually the reverse of a permanent chemically. What you're doing in a chemical relaxation is you're taking the hair that has lots of sulfide bonds in it. You're adding a mild reducing agent, not HCl and zinc, but a mild reducing agent that's breaking the thiols, which allows that hair to straighten out. And if you force it to straighten out, right, after you treat it, then you can get straight. Of course, you can also heat straighten your hair. My wife does this every once in a while. She'll, when she goes to the hairdresser, she'll get her hair blown out and heat straighten. But as soon as she takes a shower and washes her hair, then it goes back to curly, very curly. And then so you kind of have those themes. So real world analysis of that, you'll see this when you get to biochemistry, which is the disulfide bridges, as Bruno pointed out. And really it's just the ability of the proteins to create these covalent links to maintain their structure. Something that's covalently linked like this would be more stable than something that's just hydrogen bonding. Oh, I'm sorry. That was Bornface said that. So thank you, Bornface. Okay, so let's move forward. All right, so we looked at preparation of the disulfides. You again will see this quite a bit in biochemistry. So let's look at preparation of sulfides. And we can call this a reaction of thiols So what we're going to do in this one is prepare the sulfide, sorry, I'll get stuck there, by reacting something with a good leaving group. With a thioate. Sometimes this will be drawn the other way. You'll see this reacted with the sodium hydroxide, followed by the electrophilic group. And you end up, in this case, I use the same two groups, so you end up with the same group. So reaction of thiols can be used to make sulfides. If we look at the mechanism on this one, remember the pK difference between the oxygen and sulfur. The sulfur is much more acidic, much more stable as a negative. So therefore this will be quantitative. So we'll go ahead and deprotonate all of the sulfurs. No, this is not supposed to be a radical. That was a stray pen mark. Thanks for catching that. All right, so we see here, and then, so we make the thioate, and then we get a SN2 reaction. And again, the sulfur is going to be a good nucleophile, a great nucleophile, but a poor base. So we can even do this with with secondary carbons. So we get a proton transfer. To get our thiol. Okay, questions about these? Okay, so we've gone through several of these, so let's do a try this real quick before we move on to reactions of thiol, of sulfides. Okay, let's take a minute. Let's look at these three. Okay, let's take a look. Okay, so in the first one, right, we know the sodium is positive, the sulfur is negative. It's a good nucleophile, so we get a backside attack on our electrophilic group. So we get the sulfur. I was going to show the other products, but that's not necessary. So we get inversion here. Okay, on this next one. And for this one, let's break this down so you understand why we didn't get inversion here. So if we look at our mechanism, the first step is going to be deprotonation. We get the deprotonation there. right? So we haven't changed, oh, let me put the stereochemistry. So we didn't do a reaction at the chiral carbon, right? So then in the next step, that's where we get the bromine attack. Oh, sorry, I moved reactions. That's where we get the methyl iodide. And so then the sulfur is attacking the carbon, right? That's where we would get the inversion, not at the carbon to sulfur at the beginning. And so we retain that one because we've never broken it. All right. Okay, but we get the sulfide. And then the last one, we get the disulfide. But notice here, right, this is going to create a disulfide reaction. Right, I start with a thiol. I have the sodium hydroxide and bromine, which is a mild oxidant, right? And look, 1, 2, 3, 4, 5, 6. So I'll be able to create an intramolecular reaction, right? Not the prettiest drawing in the world, but I'll create an intramolecular disulfide. Now, for intramoleculars, you have to think about what would be a stable ring system. A 6 is stable, 6 is stable. I mean, 5 is stable, 6 is stable, 7 is stable, 8 would be stable, but 4 probably not, and of course 3 no, right? So you can't have internal disulfide bonds. Okay. Questions about any of these? All right, so the main reactions we have for thiols is actually creating sulfides and creating disulfides. So our main reaction for thiols is this. Of course, thiols are like alcohols. They have their own kind of thing, but we think about reactions. You create a thiol to create potentially a disulfide or a sulfide. Now, reactions of sulfides. One of the first reactions of a sulfide is just as a nucleophile. So the sulfur is still nucleophilic. So it can do a reaction and react with electrophilic carbons. So the anion is going to be more nucleophilic, but even the lone pair on the sulfur is going to be more nucleophilic than oxygen, right? So this is a more nucleophilic species than oxygen. And its stability with that third carbon there, right? It's more stable. So this is a species that I could, potentially put in a bottle, usually make it in situ. Now, what this is used for is methylation. So methylation is a common biological reaction. Now, you want to make sure that it goes in the right place, but if I have a nucleophile, right, that nucleophile can pick up the sulfur, the carbon, and kick the sulfur back off, creating now the methylation, right? I've added a methyl to my nucleophile, and then just release the dimethyl in this case. Where you're going to see this most common in a later chapter is SAM, So this is a biological. And you might see that in enzymes in biochemistry, as you'll see SAM on there. And what you should watch for is either methylation or alkylation. But the main component of that actually does the job is this sulfur. So this is just sulfides acting as nucleophiles with electrophilic carbons, creating these positive sulfur compounds. These positive sulfur compounds become methylating agents. And the one that you'll see in biochemistry or later on in biology courses is going to be SAM. And it's an aniline, it's sulfur-containing aniline compound. Okay. Can't remember the name of it right now. Okay, the other reaction you're going to see for sulfides is oxidation. Now, the big difference between sulfur and oxygen is that the sulfur can be hypervalent, right? So we can actually change the sulfur and we can oxidize it, which wasn't really a possibility. We go to the peroxide, but the peroxide wasn't really stable. In sulfides, we can oxidize the sulfides up and we can create stable compounds. So if we take generic sulfide, react that with an oxidant, we can end up with the carbonyl species, which is known as the sulfoxide. And then if we do another oxidation, right, we'll end up with the sulfone. And we've seen this before, right? We've seen you know, if we take a ketone and react that with ozone, we're going to end up getting the ozonide. And then one of the ways to move forward in that is a mild reducing agent. And we can use the DMS, right, dimethyl sulfide. That dimethyl sulfide is going to end up giving us the ketone plus the aldehyde plus then the, so we hadn't focused on this, right, because it might made DMSO, and that wasn't what we were focused on. We were focused on these reactants, right? So in this process, we actually have already seen an oxidation of a sulfide, and here DMS can become DMSO, right, to the sulfone. The sulfoxide by reacting with the ozonide. Of course, that's not the primary focus of it, but it is important to go ahead and show it. If we wanted to do this, there's a couple of other oxidants we could use. So let's look at those. So we could take we can use sodium iodate. And this is not sodium iodine powder. This is sodium iodate. And get the single oxidation up to the sulfoxide. We need a stronger oxidant. It turns out that hydrogen peroxide, you need two of these, right? But you'll often see this just shown as hydrogen peroxide in excess. This will give us our sulfone. Questions about these? Sorry, I missed that question. Sulfone. Yeah. Okay, well, that's our thiols, disulfides, and sulfide reactions, right? So preparation, we make thiols. Let's go all the way back. Don't look at the screen too fast. Okay, so if we look at thiols, we make thiols from SN1 and SN2 reactions with either sodium thioate or dihydrogen sulfide here. Then the reactions of those, we can make disulfides from thiols, right? So take thiols with a basic mildly oxidative solution to make the disulfide. Reactions of disulfides, the main reaction is to convert them back into thiols with a mild reducing agent, mercury and zinc. Preparation of sulfides, that's another reaction of thiols, right? We do that by just reacting it with the anionic thiol, right? So thioate. And so we can do that by taking the bromide and reacting the thioate, or we can take the thiol reacted with base and electrophile to get us our product. And then reactions of sulfides, we can have the methylation reaction, where we create a methylating reagent by reacting the sulfide with an electrophilic group with a good leaving group, making methylating agents. Okay. And then we can do oxidations. So there's two stages up from sulfide. So we go sulfoxide and sulfone. And then we've seen this once before. And then the two reagents, the sodium iodate, right, creates the sulfoxide, and the hydrogen peroxide can create the sulfone. Okay, in the chapter, it then gets into synthesis strategies. No, you would want to use zinc and acid. Mercury came from the standpoint of these are known as mercaptans because of the reduction of because sulfur-containing compounds will ligate to mercury well. So that's where the mercury came from. No, you just want a mild reducing agent. So acid and zinc is what you want to use for reduction to the disulfides. Of course, there's others. And if you go look at the ingredients on a relaxation chemicals, they're not going to say acid and zinc. Okay, but for here, this is what we use in the lab. It's easy to find zinc around the lab and HCl. So one of the big synthetic strategies out of this chapter we've already alluded to, which is if I have, how can I look at, the possibility of, and I'll just give an example here. How do we go from here and here? Right, and the difference here of using the aldehyde, right, which means we get a reaction at that one position, and the reaction with the epoxide, where we can add to this position, but then the oxygen is going to break, right? So that we get a 1,2 where we've added to the 1. right? But functional group on the 2. That should be on the, no, that's not eraser, on the 2. Because of the ring openings, right, of aromatics, of the epoxides, it just needs a nucleophile. There's several ways to use this strategy to come up with our product. Okay. So not only diols are this, but we can see several different ways to create those. So let's look at a few possibilities. Let's do some retrosynthesis. I think we'll be able to get through maybe 2. So okay, so let's take a minute to look at these 2 retrosynthesis. Again, think about your process before you think about your reagents. Okay, let's go ahead and take let's break down this first one. Okay, we start with an alkane, right? And we're going to this diol, this alcohol and thiol. So we have this alcohol thiol species. Okay, well, we need to add functional group, right? So we need to take this to something with a functional group, and really for the alkane, we only have one reaction, which is this. Then if we think about the fact that we have this 1,2 here, at some point, we probably need to get to the alkene, right? Because that gives us functionalities not on 1 carbon, but 2 carbons, right? So think about that. I've got 2 additions. So what I've gone from is no functionalities in the alkane, it's just an alkane, right? None to 1 to now I have 2 possible. Well, to get 2 possible, I'm going to need to keep 2. So I don't want to add just the alcohol because that it goes back to 1, right? So I've gone from 0 to 1 to 2. So I want to go now to another 2. And the one that I'm aware of, right, is the epoxide. That still gives me 2 functional sites, right? 1 and 2. And then here, I should be able to ring open that. Okay, to give us room, I'm gonna give the answer a little bit lower. So we start with this. We're going to react that with our radical bromination, right, to get the bromine, and then I'm going to do, DBU or something like that to give me the elimination. I could have also used an alkoxide. And then I'm going to do the epoxidation. You know, I've got several there, but it has to be a peroxy acid. So MCPBA is a good one. That gets me to the epoxide, right? And again, the epoxide would be at the bottom or the top, but I'm going to say from the top, because then I'm going to use sodium thiol followed by water, because I need a proton source to get me to the product. Okay, questions about this one? Okay. In the second one, we look like we are, again, if we number this, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it looks like I'm adding an oxygen to the 4 position, right? And I'm adding a methyl to the 3 position. Okay. So I want to take my alkene to a place where I have the possibility of keeping those separate. If I had added alcohol, I would have gone from 3 and 4 to 3, right? And then I wouldn't have had any reactivity on 4. So the way to do that is to go through the epoxide, because that still keeps me with this 3-4 arrangement, and then go to the addition, right? So the epoxide, also an important thing about the epoxides is it maintains that 1-2 type functionality that I could lose if I just went to an addition product that only added to one of the 2 carbons. So here again, we could use several of the reagents. I'm going to use just the peracetic acid group. That's going to form the epoxide right there. And then this is symmetric, which makes it nice. I'm only adding 1 carbon, so I can add the Grignard with 1 carbon. That's going to be the first step. All right, so I get ring opening, and then second step, I could have shown these all in one. I'm going to, you need a proton source. All right, so you add water.